in order for us to study thermodynamic processes, which we'll be doing in a couple chapters, we need to review the properties of a macroscopic system. So let's say you were to introduce a gas into a container. So I'm going to use this little pump and pump gas particles into the container until it uniformly fills out the container. You may notice on the right side we have a number of parameters that we use to characterize the macroscopic system. These are called state variables. So we could measure the volume. Typically in physics we measure it in meters cubed. The temperature in Kelvin. The pressure in physics we measure in pascals or in atmospheres. And you also have the mass of the gas or the mass of the particles, the number of molecules or the number of moles, the mass density. These are all what we call state variables. Now, if any of these state variables change in the system, then we change to a new state. So we would have, say, an initial state, and some later point in time, a final state. Now, you could change these states by, for example, heating the system, and suddenly you notice the temperature and the pressure are changing. You could add more particles, which adds the number of moles in there. So any of these state variables change, then you have moved to a new system. For the system to remain in thermal equilibrium, you need to make sure that all of these variables remain constant. All right, so we're going to be dealing with ideal gases, and obviously this is just a solid, and these atoms are just vibrating. It's not a gas. Here's a liquid, just to review some things that you had learned hopefully earlier in your science classes. And now here's a gas. These are just neon gases, but we also have oxygen molecules, which are diatomic molecules. All right, and if you take a gas at normal atmospheric pressure and something that is relatively low density, so that means their particles are very like point-like, then we can assume that we have an ideal gas. Most gases at room temperature at atmospheric pressure can be approximated as an ideal gas. And I'll get into that a little bit later on when we get into the kinetic theory model. So let's review some things that you should have hopefully learned in chemistry class. So from your chemistry class, you should have learned about the atom. And hopefully you remember that in the nucleus of the atom, we have neutrons and protons. And outside of the nucleus, we have the electrons. You hopefully had learned about the mass of an atom is determined primarily by the sum of the mass of the neutrons and the protons. That was known as the atomic mass number, which we represented with an A. So maybe I'll jump over to my nuclear physics notes for a moment, and we'll get to this later on when we start studying nuclear physics. But if you think of nuclei, nuclei can be represented using this notation. So the X here represents the symbol of the element that you're looking at. For example, over here, that would be oxygen. The number at the very top here with a capital letter A is the atomic mass number, so it's 16, which would be the sum of the mass of the protons and the neutrons. And the lower number here represented with the Z is the number of protons, so that is the atomic number. This atomic mass number, for example, for oxygen, which is 16, is commonly denoted using what we call the unified mass unit, or the atomic mass unit. In your chemistry class, you might have used the symbol, instead of U, you might have used the symbol AMU. So AMU is the same thing as U in physics. All right, that is, U stands for the atomic mass unit. The numerical value of an atomic mass unit is almost close to 1 U for a hydrogen atom. So if you have, for example, one hydrogen atom, let's say we have H11, the mass of that is approximately 1 U. Now, it's not exactly 1 U because really, actually, the U comes from actually the carbon-12 isotope, all right? And so we assume that this particular isotope, carbon-12, is exactly 12 atomic mass units. If you have a molecule that is a combination of 2 or more atoms, such as this one over here, carbon dioxide, then we have to add up the molecular masses of the constituents. All right, so let's take a look at example number 2 in your thermal notes. We're going to ask to find here the molecular mass, all right, in use for carbon dioxide. So we'll do part A. So in order to do this, you'll have to remember some things from chemistry. So we'll pull out your periodic table. And I just quickly found something off the internet. I look up for carbon in here and oxygen here. What I'm looking for is really the atomic mass number, which is here listed as 12 for carbon and oxygen as 16. So then the mass of one carbon atom is 12 atomic mass units, and oxygen is 16. And if we have a CO2 molecule, right on here, the mass of CO2 would be, well, there are 2 molecules of oxygen, so 2 times 16, plus we have 1 carbon atom, which is 12U. And this will give you 44 atomic mass units. Okay, so now we're going to go on to determining the number of moles, or what that means, or how to find the mass if we know how much moles we have of carbon dioxide. So we need to maybe review a little bit of the mole, which hopefully you learned last year as well in chemistry class. So remember, a gas consists of a very, very large amount of particles. And this is just a model, but there's a lot more particles than this. So it's more convenient to express the amount of gas or substance by the number of moles of matter. So first of all, the symbol that we use for mole, all right, just to represent it, just like pressure is with capital P or volume with capital V, we use a small letter N. And the units for moles, we just write MOL, abbreviating moles. All right, so a mole is just really, the way I look at it, is it's like a number. Just kind of like, a dozen is 12. So if I tell you that I have, say, a dozen carbon atoms, then you have 12 carbon atoms. All right? But the difference is that 1 mole is equivalent to 6.022 times 10 to the power 23. That's how many atoms you would have. All right? So if I have 1 mole of carbon, then I have this amount of atoms. So it's just like saying that if I have 1 dozen carbon atoms, then I have 12 carbon atoms. So this number that you see right here, maybe I'll highlight it, is known as Avogadro's number. But it's not just simply a number. It does have units, because you can see that it is a number, but per mole. So think of it as the number of atoms you get per mole, or the number of particles that you get per mole. So the number of moles is equal to the number of molecules, that's capital N here, divided by Avogadro's number, which we abbreviated with a capital N and a subscript of capital A. And down below in the notes, you can see that the molar mass is actually related to the molecular mass over here, which we were talking about earlier. We called the mass number. Now, the mass number, we were using the symbol U, but you can also think of that as grams per mole. So the molar mass, the symbol that we use here is typically a capital N. You'll see that often I'll write it as a kind of a script capital N. All right, and that is related to the number of moles. One could write the number of moles is equal to the mass of substance divided by the molar mass of substance. So in a formula, you could write the mass of the substance is just little m, and the molar mass is that big capital M. All right, maybe this will make more sense if we look at an example. So let's go back to the example we were doing before, and I'll just erase this image here. And let's take a look at the number of moles that we have, or the mass that we would have in 3 moles of carbon dioxide. So we know that the number of moles is 3 MOL, that's little n. We also know that the molecular mass is 44U, or you could write it as 44 grams per mole. Now, honestly, I don't remember this particular formula. I'd rather just solve it using sort of dimensional analysis, looking at units here. So if I'm trying to find the amount of grams, right, which I'll call that the mass, I could take 44 grams that are in 1 mole, right? And then I get to multiply by the number of moles, 3 moles. And then you can see, hopefully, that the moles will cancel out right here and here. And then all I have to do is just multiply 44 times 3, and that will give me, I believe, 132 grams. And that's how much substance I have. So try to use your techniques that you've learned earlier with dimensional analysis, kind of like when you convert kilometers per hour to meters per second, all right, in order to convert, say, from grams to moles, or grams per moles, and so forth. Okay? That's it for this example.